Many see AI as something similar to a miracle, but in fact, this miracle is managed by algorithms and mathematical laws. Where are the boundaries of the possible and what can be proved? Let's hear from the Berlin University professor, head of Stochastic Algorithms Lab and Non-Parametrical Statistics of Weierstrass University, Vladimir Spokoyny, with a presentation on AI and mathematical laws.
Okay, nice to be here. I'm a mathematician from my background, and in my group in Berlin and now in Moscow, we're studying some foundations of artificial intelligence. And probably the central question we're looking at is whether one can explain the performance and behavior of any artificial intelligence system by mathematical laws. So this is a question of the study. And first question, which we are trying to understand is what artificial intelligence system is really doing. And can we explain very popular system like deep neural networks or large language models or generative models by mathematical laws, and what these mathematical laws are? So actually, and whether if we succeed, whether we can predict the performance, explain the range and scope of applications of any artificial intelligence system. So this is the outline of the talk. My first question is what artificial intelligence is. So could one here in the room explain a few words in one sentence? What is artificial intelligence system? Any guess from you? Yeah, so, no? Okay. This is very simplified but useful answer. Actually, AI is a computer with a huge computing power and memory trained by large data available nowadays. So this is a very simplified answer, but it is useful to understand what is happening with the artificial intelligence system. Okay, now the next question. What artificial intelligence is doing? Again, any guess from the room? Predict. So another answer? Machine learning. So it's synonymous. So I would say artificial intelligence is machine learning.
Essentially, artificial intelligence does this. It does not have to follow a specific algorithm, but based on the data that it used to train and based on some input data that it receives for processing during its work, based on all that, it can make a decision, classify something as something that belongs to a target class or not, etc., depending on the task you set for it. It can be flexible.
Okay, thank you. It's a very nice attempt, but now my version. If you want to explain what artificial intelligence is doing, actually, this system or this computer try to solve some optimization problem. So this is mathematical answer. Okay? Now, again, if we look from this perspective, the next question is, what are scientists in the history who made the main contribution to artificial intelligence? Again, you can guess probably because of lack of the time, I will give you my unexpected answer. So, these are Newton, Leibniz, Gauss, Legendre, and Fisher. Okay? So, Newton and Leibniz, in the middle of 18th century, introduced a general method of optimization based on the first and second order differential calculus. Then Gauss one day developed a new method of nonlinear least square regression to solve some astronomical problem. And then, so he considered this as unfinished and didn't publish this paper. Then Legendre rediscovered this nonlinear least square method, and then Gauss developed new Gauss-Newton procedure. And Fisher, around 1920, formulated the principle of maximum likelihood, which is actually a universal method to solve statistical problem by reducing this statistical problem to optimization. This is the method of maximum likelihood. Okay, now I explain you what the essence of Fisher approach is. Actually, you have somehow the objective function you want to optimize. So Fisher suggested log likelihood as an objective function, and the method of maximum likelihood we tilde is the point of minimum of the negative log likelihood. So because it's maximum likelihood, so we want to minimize in optimization, so it's negative log likelihood is L of V. Now the next question is, this is what the procedure gets out of the data. So this L of V is based on the parameter V we want to find and the data. Data is hidden here in this log likelihood function. Now the question is, what is the truth, what we want to discover? What is the optimal parameter? And actually, Fisher shows that this truth can be formulated as another optimization problem, which is based not on the data, but on the data distribution. This means the only difference between these blue and red problems you see on the screen is that in the red problem, you take expectation of the log likelihood, which means you replace the data by their distribution. And actually, it appears that more or less all statistical procedures known nowadays can be viewed as within this framework of Fisher. And now mathematically, what this means? Mathematically, this means actually that we are looking at the problem of perturb optimization. This means the ideal solution is a red one. And the ideal parameter V star is defined by solution of the problem based on the data distribution, but we don't know this data distribution. And what any statistical method is doing, what artificial intelligence is doing, it is trying to solve empirical version of the real optimization problem. And the question is here, what is the discrepancy between V tilde and V star? So this is a mathematically perturbed optimization problem. Okay, now I will explain you what is the problem of modern statistics and what are mathematical phenomena behind of this by means of two examples. I start with a very simple example, absolutely classical. So it's about logistic regression. So what we're observing are the labels yi's and the corresponding feature vectors psi's, which are p-dimensional, where p could be big, large, or even huge. Okay, now what we want to build is to build a predictor, is a function of the feature vector, which explains the probability of the response of the label, given this feature vector. And Due to Fisher theory, the solution can be given by the maximum likelihood principle, which is written on the bottom. V tilde is a minimizer of the corresponding negative log likelihood. So this is the classical problem. And if you follow the Fisher theory, then you see that the behavior of the estimator is well understood, and in particular, you know that this root n accuracy, n is a sample size, and even the limit distribution is known and described by the Fisher information matrix here. And this is a classical result in any textbook. Now, the question is what happens in the modern setup? What is the problem nowadays? Okay, now you can think about maybe the same story as Euclidean and Lobachevsky geometry. So, I mean, for the Fisher theory, there are some assumptions here behind this. One of the major assumptions is that the P is fixed and n goes to infinity. This is the analog of Euclidean two parallel line never cross. Yeah? Only parallel line never cross. Now, in the modern statistics, the problem is that n could be probably moderate or even small, and p is huge. So this is I mean, parallel lines, not only non-parallel lines do not cross. So this is the same story. And it appears that if we change the setup, immediately new phenomena arise. And I only show you the small list of new issues, challenges, and phenomena discovered in the context of the logistic regression. And in particular, it appears that if P is larger than n, the method of maximum likelihood does not work properly. And maximum likelihood estimator even doesn't exist in some situations. And you need a kind of regularization. So the other colleagues, so Bartlett, Montanari, Sarvadagier, studied the problem of impact of the random design here, when empirical Fisher information matrix behaves not like the true Fisher information matrix. And in particular, Sir and Candace is sure showed that there is a kind of bias in the maximum likelihood estimator which actually cannot be explained by the classical Fisher theory. And this is only because of the random design. And it appears in this setup you need somehow another theory, another law. And then people discover some new phenomena. In particular, this phenomena, like double descent curve, hopefully known to you, which means if you do overfitting, at some point the quality of generalization becomes very poor. But if you increase the number of parameters, suddenly you can achieve a perfect fit and very good generalization. Again, no chance to explain this by the classical Fisher theory. And people also discovered the method of the second order developed by Newton doesn't apply here. You need to go back to the first order method, which can help in this situation. Okay, so I started with study of this problem, and it realized that this simple problem requires to develop new results and new methods in the study, which relies on different mathematical disciplines. In particular, perturbed optimization, random matrix theory, theory of random tensors, and regularization for inverse problems. So I don't have a lot of time to go through the details. So maybe I show you one result in the perturbation theory, which is depicted on the bottom. So, and it explains the discrepancy between the perturb optimization problem and the original optimization problem, so V circ minus V star. And this discrepancy is actually given by this blue term F minus 1a. I don't explain the notation, but this is what is called Newton correction. Newton develops this correction. This is the leading term of the discrepancy, and this result only apply in the right-hand side of this expression is relatively small. So this result, which is depicted here, is dimension-free. It applies in any dimension of parameter space. This means P could be arbitrary, even infinite. This result applies, only what you need is the red term is smaller than the blue one. And this gives maybe new law, so I jump over the other details, and I will explain you the main finding of our study. So what we discovered here is that the Fisher condition, that the parameter dimension is much smaller than the sample size, can be replaced by new condition, which means that effective dimension is smaller than effective sample size. So this means somehow we can define new notion of effective dimension. So you can think about effective number of parameters you need to estimate. And this effective number of parameters should be smaller than effective sample size, which is described via the eigenvalue decomposition of the Fisher information matrix. So this is a kind of new law, which is extension of the classical Fisher theory. And actually, it applies to any AI system. So, and what? So maybe I stress my view on the mathematical laws. So mathematical laws are the physical laws, like a law of Newton. If you have an apple and you leave this apple to fall, it will fall down. So this is a law. Physical law of Newton. And if you formulate the mathematical law, it should be like this. If you follow this law, it should work. Yeah? Without any training, Newton, fine-tuning. So this is because it is a law of the nature. And so we did some small simulation study only to illustrate this. And we realized, so I mean, we apply this. Actually, what is depicted here, I don't explain the setup, only point out. You see two curves, blue and pink. Okay, they look very similarly. Probably you cannot see the scale, but the blue, for the blue curve, so this is the error of estimation. You see the central point is around 3. And for red curve, which is error after first order correction, which I described in my main theorem, it is around 0.3. This means the result which I showed you really applies here and leads to improve of the accuracy by factor 10. So this is a small illustration. And then we confirm this by considering different sample size and different dimensions of the problem. So this is an example how the mathematical law apply. Now I will speak about another example, which is less trivial. It's about deep neural networks. And I will explain you something about blessing of dimension. I don't know if anybody is familiar with this curse of dimension and blessing of dimension. So for classical statistics, there is a kind of curse of dimensionality, which means the increasing of dimension makes the problem more complicated. Now we explain, by means of this example of deep neural network regression, that actually increasing of the parameter dimension can be helpful. And is helpful. And this is by mathematical study. Okay, So we are looking at the deep neural network. Again, I hope everybody is familiar with the structure. What we are doing, we have original input vector x. You can think about images. And then you are doing kind of transformation of this original vector by sequence of layers. So this x goes through the sequence of layers. At every layer, you have operation, which is multiplication by the activating matrix W, and then by applying some nonlinear unit, sigma. OK? And at the end of the day, what you are doing, you replace original vector x by this transform vector, so which is this bold x. And you are doing usual linear regression using this new feature vector. So if you have a simple shallow network, you are doing only one transformation and then apply linear regression. So this is a mathematical description of what DNN is doing. OK, now we consider the training problem. Training problem means you have data, yi, xi. For shallow network, we have just one transformation. For deep neural network, we have capital K transformations. And the method of maximum likelihood, which actually Fisher method applied here, leads to this optimization problem. We build the log likelihood, how this new transform model explains the data, and try to optimize a set of parameters to build the best prediction. OK? So this is what the training of DNN is doing. And even if you only look at the mathematical literature on this, so you see there is a huge number of papers, ton of literatures about this. None of this explain really the scopes and limits of this DNN training. So people try to reduce the complexity using the idea of manifold regression, but I am not convinced that this theory explains exactly what it's doing here. So again, we'll come back to this issue of curse of dimensionality. First of all, which dimensionality is here mean? So is it the dimension of the feature vector, or it is a number of parameters in the model? So actually, for linear models, this coincides. So, but in reality, so this curse of dimensionality means the number of parameters in the model. And if you consider deep neural networks, the number of parameters is huge because you have many layers, and any layer involves the matrix of weights or activation. So you have, for a really deep neural network, a huge number of parameters. OK? Now, what turns out here, so again, because of a lack of the time, I only state the findings we discovered. And the main finding is that the full parameter dimension, P, actually doesn't enter the accuracy guarantees. Only effective dimension matters, and also geometric property of your objective function, which you optimize, matter here. And it appears that you can replace your original problem by another problem, which is even more complicated in the sense of number of parameters. But then you improve the geometric property of your objective function, but you do not increase the effective dimension. And then suddenly you get the situation when the training procedure works well. So here is a very brief idea how we increase the dimensionality. We replace the original objective function by another objective function in which we include in the set of parameters also all the transformations So you have original vector x. You transform it at the next level. Then you transform again and again. And each time what you get is also parameter of the method. If you increase like this, it appears that the problem becomes much more, much huger dimension. But, sorry for this, important is that this objective function becomes locally convex in the vicinity of the true point. And the effective dimension of this objective function would not increase. So this means increasing the list of parameters, you achieve the situation that your optimization problem becomes more tractable. You can apply classical method of optimization, and at the same time, you have no loss in the accuracy guarantees. So this is a finding of this result. So here is a formulation. Actually, we managed to estimate each parameter of the deep neural network with the optimal accuracy. And even to get sharp risk bounds. Okay, now maybe I summarize what we discovered by these two examples. So first of all, actually, if you want to understand the behavior of any AI system, actually you have to look at the effective dimension of this problem. And this effective dimension matters. You can build a very, very huge model, doesn't matter. Important is effective dimension is smaller. Of course, computing in each example is tricky, but effective dimension is the only what matters. And this effective dimension should follow the Fisher law, which is mathematical law, which means that the effective dimension should be smaller than the sample size. Therefore, one of the conclusions here is you cannot train any AI system without data. So sometimes I see, so this is trained by no data. So this is impossible due to mathematical laws. Some information, maybe prior information, is involved in training. And second conclusion is that sometimes it is useful even further increase the dimensionality of the problem, but improve the geometric property of your objective function, particularly by making this objective function locally convex. Then you can apply the perfect machinery of optimization theory, and we know now that the optimization theory is a background for any statistical procedure. Okay, I think this is a good point to stop. Thank you.
Vladimir Spokoyny, ваши аплодисменты.
Vladimir Spokoyny, a round of applause. Thank you very much for your presentation on fundamental science. This round of applause is for you. Thank you very much.